Hey guys, I'm going to do a video today showing um, modeling as we've been doing in fractions. So we've done repeated addition modeling. Um, we've we've talked about fractional sizes of whole groups, and we've talked about area multiplication. I know that sounds like a lot going on, and just please stick with me, and I promise we'll make sense of it. So let's look at the first modeling of its repeated addition. So we got six groups of 2/3. And the kids would look at the denominator of thirds and they would make models here showing thirds like this. So there's the thirds. They don't have anything shaded in them yet. They're just open models with thirds in there. I apologize. I'm recording at school and an announcement just went on, and you also might hear some students in the other room, but I got to get this done, and this is the only time I can do it. But anyways, there's six whole groups, so 1, 2, 3, 4, 5, 6, and we're going to put 2/3 into each of them because we're going to repeatedly add 2/3. So there's 2/3 there, here's 2/3 here, 2/3 there, 2/3 here, 2/3 there, and 2/3 there. Okay, so now with what we practice in class and as the model shows, there's 2, 4, 6, 8, 10, 12. There's 12 of the thirds. This is an okay answer. It's an exact answer. It's correct, but it's not simplified. So the students now have been working on simplifying. And I use this analogy of Ezra, my son, going into his room and finding 6 cups that are almost full. So I'm going to take and I'm going to pour some from this cup and fill this cup up completely, and pour something from this cup and pour this one up completely. So now I can basically, in essence, get rid of that cup because I've filled these cups up here. This one's nice and complete, and then now I'm going to pour what's left of this, and that one's nice and complete. So get rid of those two, and I have not shown 12/3 now. I've actually shown 1, 2, 3, 4 complete cups. Well, that's modeling it where the whole number comes first times the fraction. And I talked to the kids where multiplication is commutative, so it's completely fine if this is your strategy for solving, and this is your go-to model, and maybe even this model that I'm getting ready to show here is kind of confusing to you. Well, but some of the word problems don't lend themselves to like repeatedly adding 2/3. Let me just go ahead and show it. So we had this problem in class where Brandon had 6 eggs. There's egg number 1, there's egg number 2, there's egg number 3, 4. Make sure I'm not gonna run off on the recording there. Egg 5 and egg number 6. My kids in class will get triggered because that's kind of going off of the line there, but hey, there's my 6 eggs. Not perfect, but they're trying to be eggs. Now, already, this modeling and this modeling look different because these are my 6 whole objects broken into thirds already. And over here, I told the kids, would it make sense to break the eggs into thirds? And if you have a raw egg, you're not going to be able to break it into thirds. So I told them, I said, guys, let's see if we can put it into 3 equal groups. Let's see if we can make them into thirds. So then the kids put them into 3 equal groups where there's 3 groups with 2 eggs in each, okay? And in this 1/3, one of the 3 groups, there's 2 eggs. And then in this group, that will be 2 of the 3 groups. There's 1, 2, 3, 4. There's 4 eggs. Okay? So that model, it shows a very different perspective of the fraction multiplication. Still though, they both get an answer of 4. But this is the repeated addition model, and this is looking at like a fractional set of a whole. The only time that this changes is when they're looking at the word problem. So the word problem would change the context. In class today and in yesterday, we worked on things like this. Like say 2/3 times 1/4. Now there's a fraction times a fraction. And what do we do with that? How would we model this multiplication sentence? Well, the students worked on looking at the denominators here, 3 and 4, as area. So we're going to look at an area multiplication view. So they take the denominator 3 here, and they go down 3 boxes, and they're going to make a 3 by 4, 2, 3, 4, 1, 2, 3, 4. They're going to make a 3 by 4 rectangle, and going to show thirds and fourths in this rectangle. And I know it seems kind of crazy, but I promise it works, and the students have been showing success with it. But anyways, let's look at our rows over here. Our rows are showing 1, 2, 3 rows. And if I break it up like this, if I break it up like that, it's showing a picture of thirds. Some of the students kind of got a little confused when I did that though, so I showed them this. Let's imagine we cover up all those boxes, because sometimes those extra boxes in there can kind of get confusing. So let's look at it like this. Let's still make that 4 by 3, so it's the same size. Let's break it up into thirds like that. And in this case, the student can see, oh yeah, it's the same image there, but I'm just ignoring all those extra lines in there. So I'm going to shade 2/3. I'm going to shade 2/3 of that rectangular area. So there's 2/3. And that's what it looks like on this image. So I can see that it's 2 of those long rectangular sections. And then just imagine putting that right here on this guy. Because I had some of the kids like shading in this right here as 2 boxes. And they're seeing 2 and they shade in 2. But as we just proved with this image here, that's not equivalent to 2/3. This is 2/3 here, so this would be 1/3, regardless of how many boxes. Those boxes will come into play here in a second when we talk about the new numerator that's formed by multiplying thirds and fourths. But anyways, to be continued, right? There's my 2/3 of that picture. Now I'm going to come in and I'm going to shade in 1/4 of it. Okay? And just like my image was showing 3 rows, I have 1, 2, 3, 4 columns going down that way, showing fourths. Well, if that was confusing for them to see thirds, I could imagine that it's also confusing for them to see fourths. So I provided the students with this template, and this is just looking at a fourth view. It's not looking at the third, so there's not the extra confusing lines. And with that, now they have the ability to color in 1/4. To use this model as it's meant to be used, I'm going to have them not shade in with their pencil, but just put lines in there, kind of mark up 1/4 with a different colored lines. So again, that's what it's going to look like without the grids and everything else. So then we can just imagine that would be 3/4, that would be 2/4, and this would be 1 of those fourths. And there we go. So there's an overlapping section going on here. There's some up here, 3 boxes with nothing, 1 box with only red, and then 2, 4, 6 boxes with gray. Those don't mean anything. What we're looking for is 1/4, this 1/4 section of what 2/3 is. And we're only looking at these 2 boxes here that have both red and pencil colorings in them. There's 2 of them. But the area kind of in reference to the whole, if you will, made by thirds and fourths, makes a new denominator. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 2 12s. I know, right? You're thinking to yourself, oh my goodness, this is crazy. But the reason we're doing this right here is to prove to the kids why this algorithm actually makes sense. So I connected that right there to the algorithm in class. So we looked at this. We said 2 thirds times 1/4. We used the same example, and I showed them. I said, okay, when we're using the algorithm to solve it, you basically squish these fractions together, making a long fraction bar. Put your multiplication symbol up top and down on the bottom for the denominators. And with this model, we did a 3 by 4. We made a 3 by 4 with that model. And just how the algorithm goes, you put the numerators on the top, the denominators on the bottom. Still the fraction 2 thirds is there, and the fraction 1/4 is there. But what we did is we squished them together onto one fraction bar, multiply 2 times 1 to get 2, and multiply 3 times 4 to get 12. And 2 12s here matches up what we got, and our algorithm right there is 2 12s. So that's a lot. I know it's a lot. But right there, I've provided 3 models from the previous models. What happens when we have a whole number and a fraction? What it looks like in word problems sometimes if the fraction is first and the whole number is second. When it doesn't make sense to break up raw eggs. Knowing, though, that both of these still provide the same answer. So if students, this is their go-to, I'm fine with that. I'm fine with that. I do want students to understand the reason why we use problems like this sometimes. In class, sometimes we're like, are you going to break up students? Like if this were not an egg but a student, it would make sense to break them up into thirds. You can't do that. Some word problems you have to, you can't go to this type of model. But still, though, with solving it, I'm fine with them using it. Over here, are we always going to use this model here to show the problem? No. But making the connection of area and fractions is fraction multiplication, I'm sorry. Making that connection of area to fraction multiplication is very, very important for students to understand why this algorithm works. Why this algorithm works right here. So anyways, hopefully that's helpful. And as always, if you have any questions, please let me know. Thank you.